So we are in Workshop 5 and we have completed step 8, which was to look at the influence on the spectrum of reducing the sample length, so using a shorter time series, and looking at how that impacts on the resolution. So moving on to step 9 now, and the aim of step 9 is to look at the influence of the sampling rate. So in this case here, we're sampling at 96 samples a second, and what I'd like you to see is the impact of reducing the sampling rate, and we'll have a look at what happens to the spectrum. Okay, so let's just try reducing the sampling rate. So at the moment we've got 96 samples a second. So I'll just minimize these windows in case we want to. I'll keep actually the original one up there, but I'll just reduce or minimize these two from the last step. Okay, and so what we want to do is to call our function find PSD FFT. Let's go up here to have a look at it again, and we want to give it a different sample rate here, fs, and we want to give it another time series which has been undersampled. Okay, so the moment we've got 96 samples per second, per day, 96 samples per day, that's what I'm talking about. And we want to reduce that by, so I'm going to suggest let's reduce it to 24 samples a day, because that's a quarter of 96. Okay, and so if we try sampling at a slower sample rate, so 1 every hour effectively, then how does that impact on our Fourier transform? So let's try calling the same function again, okay, except this time we're not going to pass it the same sample rate, we are going to pass it a slower sample rate, and I've suggested that we divide it by 4, so that will give us 24 samples per day. And in this case here, we want to then sample every 4th data point. Okay, so we can end up with a quarter of the full number. So we want to go from the first element in the array y, and we'll jump along in 4s up to the end. Okay, and then I need another bracket on the end here. Okay, and then if we go to plot, we should be able to plot that. Let's open up a new figure, figure 4, and save and run that. Okay. So if we compare this with our original time series, which is in figure 1, now what you'll see here is that the axis in subplot 1, the axis, x-axis, goes from 0 to 14 times per day. Okay, so what we're actually looking at is a small section of the spectrum that we see in figure 1 of our original spectrum. So it isn't actually that much different, it's actually just quite a lot shorter. So the 12 here is our Nyquist frequency, which is what you'd expect. Our sample rate is 24 times per day, and our Nyquist frequency is half the sample rate, so half of 24 is 12. So that's our Nyquist frequency, which is what we expect. And so by changing the sample rate, we haven't changed the sample length, as in the number of days. So our resolution will depend on the length, but not on the sampling interval. Okay, and so what you can see then is that when we zoom in on the x-axis, then we still got the same resolution. We can still resolve these peaks from the diurnal and semi-diurnal tides, and that's because they're all within the Nyquist frequency, which is 12. Okay, now if we go back to our instructions again, so we've reduced the sample rate and we see what happens to the spectrum, which is that the spectrum gets shorter and that we get a lower Nyquist frequency. So the next question is, what is the minimum sample rate required to observe the components above? So the minimum sample rate required to observe the components above will depend on whatever that maximum frequency is. So the M4 tide here has got the shortest period, 6.21 hours, and therefore that will have the highest frequency. So we can work out the frequency for the M4 tide. Well, actually we've got the frequency worked out already in the plot PSD. Okay, so the M4 one here, FM4, if we type that in here, it'll tell us what the frequency is. So it's FM4. And so we can see that the frequency of the M4 tide is 3.8647 times per day, so nearly 4 times per day. And so that means that we need, in order to see this tide, we need to sample twice this. In other words, we need to have 2 samples within this cycle. Okay, so if we then want to find out what this is in days, oh sorry, this is actually hours, isn't it? So this is 3 point, well, that's right, this is in days, we did it in days. So yes, we did multiply by 24. Okay, so we want to then multiply this by 2 to get our minimum sample rate. Okay, so if we go FM4 times 2, okay, so the minimum sample rate that we need is 7.7295 times per day. So what that means is that our time series would be, so if we go back up to our figure 4 again, if we sampled below this, then our Nyquist frequency wouldn't actually, the spectrum would stop before we got to the M4 tide, okay, which occurs at 3.86 times per day. Okay, now let's go back to the instructions again. So change the sample rate of the time series to one that is slower than the minimum required to resolve the M4 tide and plot the spectrum. Okay, so then let's choose a really slow sample rate. If you recall, in Workshop 4 we looked at sampling 2 times a day, so every half day at a sample interval. So let's just repeat that. So that means we're doing 2 samples a day, and then we want to call our find PSD FFT function, and to get 2 samples a day, it means that we would be sampling at the sample rate divided by 48. Okay, that will give us, because we're sampling at 96, so if we divide by 48, that will give us 2 samples per day, and that means here that we want to jump up in intervals of 48 to the end. Okay, so that will give us 2 samples a day, so let's just do that. And up here I'm going to again change the figure, so we get a new figure, figure 5, save it and run it. Okay, and so obviously what you see is happening is that the spectrum is just getting shorter. Okay, if if you really wanted to illustrate this more clearly, you would use the same axes limits in this first subplot at all times, and maybe extend this a little bit so you can see how it gets truncated here as well in this middle one here. Okay, so this is the output from sampling at 0.5 times per day, so every half day, twice a day, sorry, 2 times a day, and therefore our Nyquist frequency, which is half of our sample rate, is 1. Okay, so the Nyquist frequency is 1. We can't see any of the other tidal components here. It looks like it might be resolving these components. And what I just want to do now is I'll just minimize the one in the middle and go. I would like you to compare our original time series in figure 1 with the subplot 2 in figure 5. Okay, so using the half a day sample rate. And what I think we'll do is we'll zoom in on the x-axis. So if I go to figure 1, and I go to subplot 212, hopefully it'll stay there. Yes, okay. And then if I change my axes limits to from 0 to 1 here. Okay, so I actually want to stop it off at 1 so I can compare it with the power spectrum in figure 5. Okay, so there we go, it's picking up the one of the diurnal tidal components here. I think it's 01, and then in figure 5 I want to change the axes limit so it's the same. So figure 5, subplot 212, use the same axes limits. There we go. Okay, so just to compare these two figures then, what you should notice in particular, now that we've got the same axes limits, is that it doesn't really look that much different up here. It looks a little bit noisier. That's expected in the way we've got we've got the full time series here. But what's happening when we move to lower frequencies actually is that we're getting this additional peak here. Okay, and this peak is not apparent, so we can see it's under 0.1, that peak there. And if we went back to the workshop 4 instructions, if I just open up my window, see if I can find the workshop 4 instructions. Okay, maybe I don't have it. Nope. Nope. Okay, well, if you look back at the workshop 4 instructions, where we've got the got a figure where we've undersampled, we've sampled at intervals of every 0.5 days, okay, and if you look at the figure with the pink spectrum on it, then you'll see, sorry, not pink spectrum, sorry, it's got a pink, it's an example of aliasing, okay. Effectively what this peak is the result of aliasing, where you have undersampled your spectrum and it leads to an erroneous lower frequency component appearing where there shouldn't actually be one. Okay, and that's what you can see happening right here when we don't sample not often enough. We see other frequencies, in particular lower frequencies, appearing where they shouldn't be. And I think that brings us to the end of the workshop. So for your coursework, can you please repeat these tasks? You can use a different title data set, maybe the one you used in Workshop 4 for the coursework. You don't need to do it for the 2012 data set. And so for your data set, I want you to include these ranges of figures from steps 6 to 9. So that demonstrate, so you can do something, it's up to you quite how you choose to present it, to be honest, but to show some sort of sequence of change from either reducing the sample length or reducing the sample rate. So show the impact on the power spectrum and make it clear in you might want to use a series of subplots to show that, and also indicate some tidal constituents. So you might want to pick out further tidal constituents as well and see how well those are resolved. And I'll see you at the workshop anyway, so that's it.